Miroslava, come and say hello. Please come up. Really, come here, please. Everybody, on the previous class, which was the first class, everybody sort of introduced themselves. So you should introduce yourself, say who you are, what you do. Just so.
That's all?
Well, if you have some other things you want to do, a little dance, maybe.
I'm sure you don't want to do that. I'm Miroslava, I'm an employee and I work with Oleg Group and I want to enrich my knowledge of the crystals, that's why I decided to take this class.
But you're just auditing, right? You're not registered, you're just auditing.
Yes.
Okay, good. So, Miroslava.
Hi, Miroslava.
You guys know each other?
Yeah.
Yes.
We can even speak the same language. Even three same languages.
Three?
Yeah.
What's the third? Fourth time?
No, Ukrainian, Russian, and English.
So I see.
That's three languages we can communicate.
Very good. But you knew each other before coming here? I see. Good.
Well, I mean, before coming in this room.
But before coming to Kent?
No.
Oh, I see. So you had to. Good. Okay. All right. So, any questions before we start? Nobody has any questions?
Office hours.
Office hours. I don't have those yet. But I said I would. This is true, but I don't have them. I'll make a note. So, there's this old saying, when should you prune a tree? A tree, if you have a fruit tree, you should prune it, cut the branches off so it produces better. And the question is, when should you prune a tree? And the answer is when your knife is sharp. So with office hours is the same, when you see me in there. Those are office hours. You can come and see me, and if I'm busy, I'll tell you to go there and visit. Okay, let's get started. So the game plan is that we'll have these 75-minute lectures, right? Are you okay with that?
Yeah.
Good. So, and we'll have to change rooms. So we'll go here until 11:45, then we'll go over across the hallway to the teaching lab. It won't be quite as comfortable as this, but it's okay. There's a good blackboard there, so we'll do the rest of it there. And then I said that I will go away occasionally, and then there will be no classes, and this will already be happening pretty soon, because I will be going to Brazil next week sometime, but there may be somebody substituting for me. That's always a good experience for you guys to see how other people see things, so it's kind of a good experience. All right, so let us start. So I think most of the things are administrative things have been sorted out, so I want to start talking about actual course material. And so again, the plan is we have a kind of an introduction. I'd like to talk about estimation, just a little bit about how to estimate things, then about units, because we have to speak the same language. We have to, when we measure something, we have to use the same units so we can compare things. And then a very beautiful thing called dimensional analysis, which is something that I'm very, very fond of, because it's a very powerful way of predicting things, even though when you're not familiar with it, it looks a little strange. But anyway, it's a very beautiful thing. It's a kind of an art, and you can impress your friends if you get to be good at it. And then after that, we'll start statistical mechanics. So the first thing is this business of estimation. And the idea is that we don't know everything. As physicists, we like to imagine that we know most things, we know everything. And so often we don't know the answer to certain questions, but we should be able to estimate things relatively well. And this too is a kind of an art, and it's something that is useful to develop. And so this particular approach to things was really made popular by Enrico Fermi, who was an Italian physicist working at the University of Chicago, and he did a lot of really important work groundbreaking work in nuclear physics. And some of these problems are called Fermi problems. And if you go on the web and just look at Fermi problems, you will find this stuff. So, typical question maybe, and this is a kind of a classical one, is this: how many piano tuners are there in New York? So, I mean, I don't know, have you guys seen this problem? It's kind of a classic problem. And so, if you ask someone on the street how many piano tuners in New York, you know, they say, I have no idea. People are very fond of saying this, I have no idea. But, in fact, one can make reasonable estimates, and the idea is, of course, we can't just think and get it dead on, but we should be able to get it within an order of magnitude, within a factor of 10. And so, the argument might be that, well, you know, how many pianos are there and how often are pianos tuned? So we've got to figure out how many pianos there are in New York. So how many people in New York?
10 million.
10 million after that. So number of people, so there's 10 to the 7 people. And then you can imagine that a lot of those are families, and families often have more pianos, I think, because they have kids who have to take piano lessons. So I don't know. So how many families would there be in New York? Well, how many people in a family? So there are 3 people in a family, maybe 2.5, something like that. So if half the people belong to families, and then there are 2.5 people per family, then there may be 2 times 10 to the 6 families. And then what fraction of these would have pianos? If you think about people, you know, what fraction of families you have visited?
A quarter.
You must hang out with pretty musical. I would say maybe a 10th or even less than a 10th. Is it, huh?
I'm biased, I've always had a piano. I'm biased, I guess I've always had pianos.
So I don't know. So maybe there are. I don't know. I'm just, you know. I would guess no more than 1 in 10. So let's say that there are 2 times 10 to the 5 pianos. So of course this is just a rough guess. We don't know well, but it's not too unreasonable. And then how many times do you have to tune a piano in a year? How often do you tune a piano?
Once. Twice maybe?
Well, yeah, if you're a really serious musician, you should tune it twice. I mean, typically in the summer and winter is different, but most people, I bet, you know, do less than a year. So, you know, my guess is that there may be maybe once a year. So let's just say tune once per year. So we have 2 times 10 to the 5th piano tunings per year. Okay. So, how many working days are there? Am I moving around too much? Are you? I need to have heavy soled shoes and So, how many working days in a year? Roughly 200, if you know, there's lots of holidays and things like that. So 200 working days per year. So if you divide this by 200, then we'll get 1,000 piano tunings per working day. How many pianos can a piano tuner tune in a day? One?
Two.
One.
I think one is enough. One will make them enough money.
Yeah, pretty
It depends how much money he'll take for this.
pretty easy life if you just do one a day. They might get, you know, I mean, they use electronic pitch meters. And these are really cool, by the way. I don't know if you guys have seen these, but you can get them for any kind of instrument. You clip on and you get a little liquid crystal display, and you play the guitar string and it tells you the pitch exactly, and then you can tune it. So I think it's pretty fast, and my guess is that, you know, guys should be able to do 2 in the morning, 2 in the afternoon. So I think you should do, say, 4. One guy should be able to do, I think, 4. So that's a 5 per day per tuner. Okay, so this says that if you have full-time piano tuners, this is 1,000 divided by 5. So there should be about 200 piano tuners in New York. And I looked up once the New York Piano Tuners Guild membership, and there are 48 piano tuners in the New York Guild. Then there's piano tuners who are not in the guild. You know, so probably this is a reasonable number. So, you know, you can check it out in the other pages. But the point is that you can take something that looks on the face of it pretty inaccessible, but you can usually get an answer with an order of magnitude. And it's a really important skill to develop. It just means break it down into little pieces and just kind of use common sense arguments and see what you can come up with. And you can do this for all sorts of things, not just counting piano tuners. You know, you're walking down the street and you see these big power poles that carry these high tension electrical, high voltage electrical cables. And you see these cables hanging from insulators between posts, and you can ask yourself, what is the tension in such a cable? So let's have a go at this problem.
I would say that all the mass of that cable is in the middle, and the shape of this cable is triangle. So it's the simplest way, for example.
Well, okay, I mean, it's kind of like that, fair enough, but let's figure out what the tension is. The tension is if I were to cut mentally the cable, how much force would I have to apply to keep it in place?
Okay, so we should know what's the distance between this, how are they called?
I agree. Distance, what is the distance?
Let's say 20 meters. Is that okay?
No,
Too much?
too little.
100 meters.
100 meters.
100
20 meters is not much, 60 feet.
Well, maybe that's for, okay, a little bit 100 meters.
Maybe for a small hole.
Yeah. For small.
So, roughly speaking, let's say 100 meters. Okay, good enough. What's next?
Then we need to know how deep this
Well, yeah,
tube is. And it should be, oh, well, I don't know. I almost said it. Let it be 2 meters. No, it's not. It's a lot. No.
maybe let's talk about this angle here. But ultimately, that's really what matters, Yeah, I think that, so yeah, so this is about 45. And so, 30 maybe here. So that's about 15 degrees between my fingers and the chalk, right? So I would guess maybe it's closer to about 15 degrees, but we could have a look and go there. How would you measure it? The angle.
What's the question?
Hmm?
What's the question?
How would you
You
measure?
gotta listen.
No, I asked what you
No,
just said. The last
How would you measure the angle?
Take a measure for that thing.
Protractor.
But like,
Measure the distance in the middle part of the.
That's why, yeah, you need to know the shape of the curve. What is the shape of the curve? Triangle is sort of the first 0th order
Yeah.
iteration.
Uh-huh.
What is the actual shape? Does anyone know?
So, how you say that? You throw object out.
Is it a hyperbola?
Hyperbola?
It's not. I think it is.
well, actually, it depends how solid that rope is.
No.
Well, I mean, if it's just like
Well,
a
no, but
rope,
you could say that for a triangle too. It's a triangle, it depends on the angle.
I think to a good approximation, it's a circle.
No, it's just.
Okay, I agree.
I think it's a better circle than it is a triangle.
It's after
A circle is a better
Yeah, that's,
approximation than a
I
triangle.
don't know how to say that, but it's same trace when you throw object
trajectory
out.
of free falling.
When you
Same
throw an
trace
object,
when you throw object out.
It's a parabola.
that's a parabola.
Okay, so that's that.
I don't think it is a parabola.
It is.
This,
Is it a parabola?
arc,
Arc.
arc is just a piece of a curve.
Yeah.
But that's not very specific. You can have millions of different kinds of curves.
Maybe what the part of the circle.
Well, it's
The
part,
part of the circle.
it's part of something. I don't think it's a circle.
I don't know.
Has no one solved this problem?
Well,
The shape of a hanging chain?
Yeah,
I might have, but I don't remember.
It's a special curve. It's called a catenary, and maybe we'll solve this problem at some point. So anyway, but that just it's not directly relevant. Yeah, it is in fact you can write it in terms of hyperbolic trig functions, hyperbolic tangents. So okay, now what's the next step? We have D and A.
We
I
need
mean, if
to
I'm
mass.
mass of the cable,
That's the
mass of the cable.
Mass of the cable, what is it?
That's the immense.
Density.
And what's it? It's made from
It's made from.
Oh, yeah, well, you guys have to guess.
It's made-
right?
so it's
This
made
is
from
the whole
copper.
idea of estimation. What are these things made of?
Copper.
Copper, you think?
I think aluminium.
Does it look
Oh,
yellow?
no.
Does it-
No,
when
they
you
usually
look
look
at it,
steel.
does it look?
It's black, but it has a coating on it. It's made of a bunch of little copper wires, isn't it?
I think
A
it's
bunch of little copper wire.
Are we talking about the high power transfer or?
Yeah, the ones you see out on the
So-
roads, you see these big towers with these big cables hanging. What's the best conductor in the world? The best conductor of electricity? Besides superconductors.
Gold.
Gold. Yeah, gold is really good. Is it gold?
No.
I think it's
Okay, what else is
aluminium.
good?
Silver.
Silver's good.
No.
No.
And copper and.
Next, copper is good.
I
But
think
copper is
aluminium.
expensive. Copper is weak, right? It's expensive, it's heavy, it's weak, it's very soft, right? Comes apart easily. What's next after copper?
Aluminium.
Aluminum, right. It's aluminum. If I tell house wiring is aluminum, that's aluminum. So, what's the density of aluminum? What's the density of water?
10 to 3.
One what?
1 ton per
Gram.
cubic meter.
One what?
1 ton per cubic meter.
I think it's 11,000. Oh, aluminum should have 11, alright.
11? No, still is 6 point.
Or
2.7.
2.7 maybe.
Well, so water is 1,
Gram per cubic centimeter.
1,000 kilogram per.
right, it's 10 to the 3 kilograms a cubic meter.
Mhm.
And aluminum is heavier,
Heavier.
by a factor of,
2.
it's pretty like 2, yeah. So aluminum is pretty much 2 times 10 to the 3 kilograms per meter cube. Okay, so then, let's estimate the mass of this guy.
What's the diameter of that?
Well, it's like probably has a diameter of 15 centimeters.
No,
You don't think so?
no, it's too big. It's too big.
They're pretty big. Have you ever seen them? They're giant. They're really big.
I think about 7.
They're giant. They look small when they're up there, but they're really, really a big ass wire.
That's what somebody said, that's why the elephant's tail is so small. It's not really that small, but it's just so far away. Okay, so I don't know, so it's something. So the diameter is maybe, let's go in between you guys, 10 centimeters. Okay, but the course will get more difficult than this, okay? But I just want to sort of lead you down this path a little bit, just so you have some idea. Okay, so, all right, now, what about the length then? We need the length of the wire.
110 meters.
Well, I don't know, so we have an angle theta there, and then if you now go to the triangle approximation, then what do we have? So we have theta here, and that's L over 2. Then what is that side there? Theta.
Divided by cosine.
Right, divided by the cosine. So it's L over 2 divided by the cosine.
A little bit,
That's the double
15.
it.
No, or 10. 10. No.
So D over cos theta. Pretty good?
Okay.
Okay. All right. And so then the mass is what?
By
What is cos of 15? I don't know.
Well, I just write it down wherever the computing is here. So the mass is what then?
it's rho plus d squared plus 4 pi
D squared.
d squared
And then,
divided by 4
good, yeah, so that's R squared
and plus pi plus L.
plus
Pi.
Pi.
I mean by pi.
times, yeah.
Times,
yeah.
right, so
Times pi
pi
times
L.
the length,
2
which is D over cos theta.
Mm.
Oh, I think it's like this.
The L should be
Why do we divide
So now it's a diameter, it's not
Diameter.
the
Yeah, it's-
not-
the area is pi r squared, and R is D over 2. Is everybody okay? Yes?
the L should be 2 times 2D.
no, not
No, this,
So this length here is L over 2, this length here.
yeah.
Right? So, no, sorry, this,
D.
yeah, this is D over 2. Right? So this is L over 2, right? And that's D over 2 cos theta.
Okay, sorry.
So, okay, so now we have that. All right, so what do we have? So now we have the mass. Okay, what's attention?
It's the fold.
Thank you.
Yeah, and
How do we compute it?
the mass divided by cosine theta
By C. I think.
Why?
and by 1 because
It will be
because you have the string here and every point of the string has the same tension, right? So that's this 2 point it basically is like these 2 directions.
Yes.
And this, oh, sorry, it's not by cosine, it's by sine. So the vertical component
Yes.
of 2. So this is the tension F by Q by sine sigma equals mg.
Right.
So
So the
think about
tension-
it, this part back here. Is that right?
Wait, let's go, it's close, but let's go slowly. So there's tension here, right?
Yeah.
And then this angle here is theta, right?
Right. So we
So this guy here is T sine theta.
T sine theta. Yeah, we have 2
Okay.
to equal to
So we have 2
gravity.
T sine theta equals
The gravity.
the force of gravity pulling it down. Very good. That's it. So now we can get the tension. So T, good work, Sean, is mg over 2 sine theta. And we have the expression for m here. So we have all this complicated business. Rho d squared pi, big D, 4 cos theta, sine theta, g. And then another factor of 2. So what is cos 2 times cos theta sine theta?
Sine 2.
Sine theta.
Sine 2 theta, right? So we
Should
can
be
replace
beta.
this
Should be big.
by sine 2 theta.
There's 2.
2. No, it's 4. That's right.
Yes, no?
It's 4.
Yeah, we had a 4 and a 2, and the 2 got absorbed into the sine theta. 2 sine theta cos theta is sine 2 theta. Okay, that's it. And now sine 2 theta, we can evaluate, right?
Yeah.
So what's sine of 30 degrees?
1 over 2.
It's a half, right? Good. Okay, so we won't put the numbers in here, but we can do it, okay? So that's the idea. So you should be able to look at simple problems in the world around you and estimate things. And you should think about this. You should think about this a lot. Every time you see something, estimate it. What is the weight of a car? How many hairs on you as head? How many cells in your body? How many electrons in your body? Stuff like that. Okay? So that takes care of the estimation part of the course. I give you an assignment where I'll ask you to estimate how long is the thread that you need to make your blue jeans, things like that. So you should be able to estimate it. It's really important and really useful. It'll come in really handy. Okay, so any questions on this? And if you want to see more problems like that, then look for Fermi problems on the web. And you'll find lots of interesting things. Okay, now, I forgot to do one thing last time, and I forgot it this time, which is to ask Yuet to come and introduce herself and say a few words about her background. Because we have to get to know her, because she's your TA.
Hello everyone, my name is Yue, I'm from China, and I've been working in Professor Palffy's lab for several months, actually from the beginning of this spring. And I'm very glad to be involved in this class as a teaching assistant, and hopefully I'll be glad to grading your assignments. So everybody enjoy your study.
How did I get hold of you?
I'm always in 312 in the big office or lab or at home. You can call me.
And your email address?
It's YCUI. And my name is
Okay? Good. All right. Any questions or comments then on what we've done so far? So really think about this, okay? Try to estimate things. Just every time you see something, estimate things. Ask yourselves, see a big building. How many bathrooms are there in that building? These are good questions, an important question. As you know, there are no bathrooms on the other wing of this building. That's because initially the design called for the two buildings to be connected at the bottom. But then they changed the design. But, you know, questions like that, how many pizza delivery vehicles are there in Kent? Just try to get a sense of how to approach these problems. Okay, so, all right, the next thing then I want to talk about is dimensional analysis. And dimensional analysis is really a wonderful, wonderful thing because you can predict all kinds of things without having to do much work. And so I hope to be able to demonstrate to you how effective this scheme is. And basically the idea is very simple. You want to know something. You want to know, for example, how big a voltage you have to apply to a liquid crystal cell to make it switch. And suppose you don't know anything about liquid crystals or hardly anything about liquid crystals. So then you would ask yourself, well, imagine that somebody has done this problem and they wrote down the answer. They would say switching voltage is equal to, and that would be something on the right-hand side. And you try to guess what the something is. That's all. Okay? Well, that sounds kind of crazy, but you need to think about, what could it be? What does it depend on? It doesn't depend on the time of day, right? So presumably T doesn't go into that expression. Does it depend on the acceleration of gravity? No. So, the tricky part is to figure out what the relevant quantities are that determine the answer. So that's where the real art is. And once you identify the relevant quantities, then you say, okay, these are the things that have to come into this expression. How can we put them together to come up with something that has the right units, volts? That's it. And it's simple and it's amazingly powerful. There's this famous example of G.I. Taylor, who was a British fluid dynamicist. And when they published the pictures of one of the early nuclear tests in Life magazine, one of the most closely guarded secrets was the energy yield of this nuclear explosion. And just by looking at 3 pictures of the expanding fireball, G.I. Taylor could calculate the yield of the explosion. So you can do literally unbelievably impressive things with very little effort. But again, it's a skill that you have to work on and develop. The other reason why you may want to do this is because you will be writing exams, and there may be very occasions when you don't know the answer perfectly. Okay. But that would be a problem. Calculate something, and you'll be given some information. And if you don't know anything, you can say, how can I combine these things to give me something with the right units? And most of the time, you can get the answer that way. You may miss a factor of pi or a factor of a third, but generally you will get it pretty close. And usually that's if it's not perfect, but it's still pretty good. So it's just a really valuable thing. Now, before we can put this scheme to work, we have to agree on a system of units. So let's start by talking about this. And there are many, many units out there. There's units for everything. And it can be frighteningly complicated on the surface. But amazingly, it turns out that you only need to know 5 fundamental things, and you can express everything in the world in terms of those. Everything having to do with physics, love, for example, literature, different things. But in the physical world, everything that you can measure, you can express in terms of these 5 things. Okay, and that's great. Five is not so many. We can understand 5 things. Okay, and then these 5 things, the 5 things are, who knows what they are?
Solid, gas, nuclear crystal, crystal, and plasma.
No, I'm thinking about you're thinking about the states of matter, right? I'm thinking about fundamental units, quantities in terms of which we can express every measure.
Oh, the kilogram, the meter,
Then mass times
Second.
temperature.
So you're giving units, I'm looking for quantities right now.
okay.
So,
Mass,
right, mass,
Temperature times.
okay, so the mass, good. Then there's time, length, we need length, good.
Current.
Temperature.
Current, yeah, electric current. And temperature, right. Okay, and it turns out that that's all you need. Everything in the universe you can express in terms of these things. And that's pretty remarkable. And then there are different, so these are the basic dimensional quantities. We're going to get the vocabulary, right? So these are basic dimensional quantities. And then there are different systems of measurement where there are different units for these things. Now we'll be using the international system, the SI system, which pretty much the whole world is using, more or less. So we'll exclusively use the SI system of units, and this will make life easy for us because we won't even have to write down what the units are. We'll know automatically that if it's mass, it's kilogram. So the SI units are what? What is the unit of mass? Kilogram. It's a little funny because okay. I also want to give a symbol for this. I'll put the symbol on this side. Symbol. So the symbol of mass is M. So I'll typically write little m, and it means mass, okay? So this is different from this, right? This is a symbol for the particular unit. M is just for this basic dimensional quantity. Symbol for time, little t, and the unit of time in SI units is seconds. Yeah, so this is a little funny because kilo is 1,000. That's 1,000, so basic thing is 1,000 for something else. But that's what it is. Okay, so length, unit of length.
XYZ.
No. XYZ, no, they don't have good. Just align with things on.
L.
But that's an important point because, I mean, you can use X for a length, but it doesn't need to have units, right? It can be just some kind of dimensionless length, denoting how many points you have along the line, basically, or how many notches you have along the line. Okay, so what is the unit of length? Meters. Yeah, so that and that are different. All right, now, current.
Big I.
Big I. And the units? Ampere.
Can't current be broken down again into charge very big times.
Yeah, and that's a really good point. This, you need 5 things, but they are not unique. We could have put electric charge here, for example, would have been just as good. Or something more complicated, we could have put power here in watts, it would still work. Electrical power. So we put voltage there. So there's different schemes, but these are the accepted 5. All right, the temperature, there's big T, and the units are Kelvin. Yeah, and most of the time we'll be working with absolute temperature measured in Kelvin. That's important. Right, so sometimes there are problems. Temperature is 0 degrees C. You know, to put that into a denominator, something over KT or big trouble if you put 0 down there. So you've got to remember that typically we're working in absolute temperature. Okay, everybody happy with these? So these are the units we use, and what I claim is that everything in the known universe can be expressed in terms of these. Okay. And this is important. If you want to do dimensional analysis, you need to be able to reduce everything to the same set of 5 things, because then you can see what happens when you combine them. Okay. Otherwise, you have strange units of farads per meter, and I don't know, some other crazy thing. And you don't know what happens when you bring 2 things. Now, there are 2 other quantities which people sometimes talk about, and one of them is luminous intensity. But we don't need it, and it also has one aspect that these other things don't have, which is that it depends on the sensitivity of the human eye. So to some extent, it's a kind of a subjective quantity. It's useful when you want to talk about how bright things appear, but you don't really need it to describe phenomena which are not subjective. So luminous intensities, I won't talk about it. And the other thing that people sometimes put in here is Avogadro's number, basically. And that is no units, but people still put it in here sometimes because it's something that you should know. But we'll deal with that separately. So these 5 things are the only things that you need to be able to express any physical quantity. And before we really get involved in dimensional analysis, I'd like to talk a little about that. It's how to take any kind of a physical quantity and convert it into these guys. Okay, now, everybody happy with this so far? Okay. Now, I think it's almost time for us to go over to the other room because people will be coming in here soon. So let's do that.